So here's lemma 1. Lemma 1 of Croot, Lev, and Pach. So lemma 1 says, let the following conditions hold. Let n be an element of the integers greater than 1, the set of integers that are greater than 1, greater than or equal to 1. Let d be an element of the set of integers that are greater than or equal to 0. Let p be a multilinear polynomial in invariables of total degree 1, of total degree, sorry, not total degree 1, total degree d, and it's a polynomial over some field f. And that just means that the coefficients of each of the terms in P are elements of f, the field f. And lastly, let A be some subset of the set f in this field. So this is equal to f cross cross f, so this in times, and moreover, the cardinality of A is strictly greater than 2 times the sum from I equals 0 to d over 2, and I'll write the floor of d over 2, because we don't know that d is even, of n choose I. So suppose all of these conditions hold, then we can say the following. So then the following implication holds. P of A minus B equaling 0 for all A, B in A, with A not equal to B, this condition right here implies that P of 0 is equal to 0. And to get our head wrapped around the statement of this lemma, let's first just consider the case when n is equal to 2, when d is equal to 2, and when f, the field f, is just the real numbers. The real numbers is a field under multiplication, under the usual multiplication and addition. Oh, and by the way, this should say of total degree at most d. So P is a multilinear polynomial in invariables of total degree at most d over some field f. In this case, we're considering the field of real numbers. So one of the first things, the proof of the lemma stage. So let's get into the proof of this lemma so that we can actually better understand the statement by looking at the proof. So the proof sort of starts out by saying, hey, we know we're dealing with these multilinear polynomials, and we're going to be evaluating these multilinear polynomials at n-dimensional vectors. So instead of making a mess of indices, we're going to define what actually is a very elegant sort of notation. So they're going to define this notation as follows. If I have a n-dimensional vector x, so x has n components, then if I write x raised to some I, where I, so let I be a subset of the positive integers up to n, then this is just the product of, for all I and I, of the ith components of the vector x. Oh, and by the way, since we're dealing with polynomials over a field f, this polynomial is an element of Fn. So let's look at an example here. In our case, remember our toy example has n equal to 2. And let's consider a vector A with 2 components. So this is, remember our field, we let our field be R. So this vector is an element of R2. So if we wrote, for instance, A raised to the singleton 1 power. You can think of it like that. This is singleton 1 power, the set containing the 1, then this would be just equal to A1. Or another example would be A raised to the empty set. What would this be? Well, this is the empty product, the product of 0 elements. We define that to be just 1. And let's do one more. So if we raise A to the 1, 2, the set containing 1, 2, this would be A1 times A2. And the last little bit of setup work that they do before they get into the main claims of the lemma is they let M, let me change colors here, they let M equal the sum from I equals 0 to D over 2, and I'll write the floor of D over 2, but remember in our little toy example, D is equal to 2, so we wouldn't really have to write D over 2 in our toy, the floor of D over 2 in our toy example, but they define M to be the sum from I equals 0 to the floor of D over 2 of N choose I. So let's look at our little toy example. If our toy example, our D is equal to 2, so this means our M in our little toy example is equal to the sum from I equals 0 to just 1 of 2 choose I, since our N is equal to 2. And this would just be 2 choose 0 plus 2 choose 1. 2 choose 0 is just 1, and the number of ways to choose 0 elements from a 2-element set is just 1. There's only one way to choose nothing. And then the number of ways to choose the number of ways to choose 1 element from a 2-element set is 2. So our M in our little toy example would be 3. And finally, they define this family. They define this family of subsets K. And they're M subsets in this family. K1, K2, Km. So, again, in our toy example, our family would look like this. It would be K1, K2, and K3. And then also, they say furthermore, for every I, Ki has order, has cardinality less than or equal to D over 2. And each Ki is a subset of the positive integers up to n. So in our case, what would be the three K1, K2, and K3? What would be the 3 elements in this family for our case when n equals 2 and D equals 2? Well, they would just be the singletons. So K would equal, script K would equal the singletons 1, 2, and then the empty set. The empty set as well, because the empty set has cardinality less than or equal to 1, because in our case D is equal to 2, so D over 2 would just be 1. And it's certainly a subset. It's a subset of every set, so it's certainly a subset of the positive integers up to 2. So now we finally have our setup, and we're ready to get into the first few claims of the proof.